Hello and welcome back to Physics 141 Classical Electromagnetism 1. So we are now on the third lesson for this chapter. So before we proceed with the lesson, let's review some of the concepts that we have discussed so far and the concepts that we need for this lesson. So let's recall the Laplace equation in Cartesian coordinates. So it's basically just a second order partial differential equation. So, and it's all, or the Laplace is essentially the Laplacian of V, and it's equal to 0. We also need to recall about the boundary conditions. So these are just some of the generic boundary conditions. So if you have a grounded conducting surface, grounded metal surface, then that means that the potential there is 0. So boundary conditions are just the conditions or the values, specifications of the potential at the boundary. So for instance, another common generic boundary condition is when R approaches infinity, then your potential must also approach at to infinity. Since take note, the potential is inversely proportional to R, so that means at infinity it will also approach to 0. And because of that, since the potential V depends inversely on R, when R approaches 0, if you look up, if you take the Coulomb's law equation, for example, kq over r, at r is equal to 0, the potential becomes infinite. But we can actually set a condition for that even though r will approach to 0, the potential must be finite. It must not blow up at r is equal to 0, because we will have a black hole inside your, for example, if you have a spherical charge spherical symmetry, then at the center of the sphere will be a black hole. There will be an undefined or an infinite potential. So we must, to get rid of that scenario, we must set a boundary condition that when r approaches 0, the potential must be finite. So our lesson for this session will now be on the separation of variables. We will divide the separation of variables lesson into two, in Cartesian coordinates and in spherical and cylindrical coordinates, because this is a very long discussion. So this technique in finding the potential, called separation of variables, is one of the very useful techniques in solving partial differential equations. So let's now start our lesson. So the separation of variable technique is a direct solution to the Laplace equation. So this is our favorite tool for solving partial differential equation, and it's only applicable, of course, if you are given the potential at the boundaries, or there are specified boundary conditions. So in this technique, we usually look for solutions that are product of functions of each coordinate. So for instance, in Cartesian coordinate, this is the Laplace equation. We will assume that the potential, three-dimensional potential, as a function of x, y, and z, is just a product of three functions, x, y, and z, which is individually a function only of one coordinate. So usually we call this solution as the separable solution, or we say that the potential is separable in x, y, and z. So this is the main assumption in the separation of variables technique. So you assume that your solution potential is just a product of three functions of the three coordinates. So in the solution to the Laplace equation, in general, the solutions are complete and orthogonal. So we emphasize here solutions because there could be more than one solution. So if there are more than one solution, say V1 is a solution, V2 is a solution, and V3 is a solution. If you will recall in your linear algebra or in your mathematical physics, if there are many solutions to an equation, then a combination of them is also a solution. So in general, if V1, V2, V3 up to Vn is a solution, then any combination of them is also a solution. So specifically, this is a linear combination, and the C here, Cn's, C1, C2, C3, C4 are what we call the linear combination coefficients. So this property is what we call the completeness property of the potential V, or the solution. Our solutions are complete because any solution can be written as a linear combination of other solutions. So that one. So our general potential function or general solution will also look like this. It will be, if you have more than one solution for the Laplace equation, then you must combine all of those solutions. So our general solution will look like a summation or a linear combination of all the solutions. So the second property of the solution is they are orthogonal. So meaning, if you integrate one solution and another solution over another solution, basically this is just the definition of that product, or what's another term for that product? But yeah, that product. So basically, this is an integral version of that product. So if you dot the two solutions, since they are orthogonal, then their answer must be 0. Just like I hat dot j hat is equal to 0 because they are orthogonal. So this is the orthogonality condition. So in this lesson, we will encounter mostly orthogonality conditions in sines and cosines. So this is the orthogonality condition for sine. So if your potential solutions is sinusoidal, then the orthogonality relation between two solutions is, this integral is just equal to a over 2, but you have a Dirac delta here. Sorry, a Kronecker delta here. A Kronecker delta can have a value of 1 or 0. This is 1 if n is equal to n prime. This is 0 if n is not equal to n prime. So meaning, unless n here is equal to n prime, it's the same, unless it's the same solution, or unless it's a dot product with itself, then it's 0. So just like I hat, just like the dot product, that's the property of dot product. You can only have a value of 1 or 0 for the dot product. So that's the Kronecker delta here. Similarly for cosine, you have that orthogonality condition, and if you have, of course, sine and cosine, those are clearly different solutions, then they are orthogonal. So this dot product is 0. So let's proceed directly to example so that we can directly experience how to do or how to solve a problem, a potential problem, using the separation of variables in Cartesian coordinates. So in this example, we have two infinite and parallel grounded metal plates. So these are infinite. So these metal plates extend to infinity. So you have the lower plate at y is equal to 0, and then you have an upper plate at y is equal to a. So these two plates are in the xz plane, and you connect the two plates with an insulating strip, this black strip here, at x is equal to 0, So this is in the YZ plane now, and the potential there for the insulating strip is V naught, which is not yet specified, but it's a function of y. So we are then asked to find the potential between the plates, or inside the slot here. So again, by the way, the purpose of this insulating strip is to prevent the two plates from shorting out. Take note, if you have a grounded conducting plane, you have an induced charge on the plane. There are charges on the plane. So if the two planes touch, since these are conductors, there could be a flow of charges, or a mix-up of charges. So the insulating strip makes sure that these two plates have no physical contact. Okay, in the technique called separation of variables, the first step in the solution is to always write down the boundary conditions first. So let's try to write the boundary conditions first. So what are the boundary conditions for this problem? So obviously we have the generic boundary condition that when x approaches infinity, the potential there must also approach to 0. And at y is equal to 0, so we are talking about this lower plate here. So the potential must be 0 because that's a grounded conducting metal plate. And at y is equal to a, so we are talking about the upper plate now. At y is equal to a, so the potential must also be equal to 0. And at x is equal to 0, so we are now talking about this insulating strip here, this plane here. At x is equal to 0, the potential there must be equal to V naught, which could be a function of y. So it's not yet specified, but we will try to specify V naught as a function of y later. So obviously from the boundary conditions, you will notice that the potential doesn't depend on z. Actually, you can add a boundary condition that when z approaches infinity, the potential must also approach to 0, but that's just a generic boundary condition. The boundary condition that matters here are these three boundary conditions: boundary condition 2, 3, and 4, which are all about x and y. So which is also what you can see here. So in situations like this, we actually have a symmetry along the z-axis. So there's a symmetry along the z-axis, which means the potential doesn't depend on z, and it only depends on x and y. So basically this is just a two-dimensional Laplace equation problem. So two-dimensional problem. Okay, so what we will do, so this is now our Laplace equation. So we substitute our v here, which is x and y here. So upon substituting, so v is equal to x and y, and since in the first term, for example, since y does not depend on x because y is only a function of y, then you can take y out of the differentiation, and what happens is the partial differentiation becomes a total differentiation because you are now only differentiating the function x, which is only a function of one variable x. So that one. So we take out y out of the differentiation, and then the partial differential equation becomes a total differentiation because x here is now a function of one variable x. So it's now a total derivative, no longer a partial derivative. And then we divide both sides by v or by xy. So divide both sides of the equation by xy. So divided by xy, so you will get 1 over x here. You divide this by xy, you will get 1 over y. And then you transpose that to the other side of the equation, and you will get this. So if you will notice, this side of the equation is only a function of x, and this side of the equation is only a function of y. And what could that mean? One one side of the equation is only purely x and the other side of the equation is purely y. What can you tell about the two if you have something like this? Sorry, y. So you notice that if you take the derivative of the equation with respect to x, so you have partial of f with respect to x, then you have partial of g with respect to x. So of course, partial of f with respect to x, sorry, not partial but total, because this we are differentiating with respect to x, for instance. So since f depends on x, then it could have a partial derivative, but total derivative. But in the other side of the equation, g is only a function of y. So if you take the differentiation with respect to x, then you will get 0. So what does this tell you? If the derivative of f with respect to x is equal to 0, then this means that f is a constant, or g is a constant. So meaning this is all equal to a constant. That's the only way to satisfy this equation. It can only be a constant. So we will let our constant as, say, k squared for reasons that will appear later. So you will have this equation now. So we will now have two differential equation. Differential equation next, this one, which is equal to k squared. So we just cross multiply x there to have to formalize our equation, and we will also cross multiply y here. So we will now get these two differential equations. So the differential equation for x and the differential equation for y. So this is what we mean by separable solution. You can actually separate the Laplace equation into it depends if it's a two-dimensional. In this case, a two-dimensional Laplace equation, we have actually separated it into two ordinary differential equations. So from a partial differential equation, we have separated it into two ordinary differential equations. So of course you have already you already know how to solve this problem. Well, if you don't know how to solve this problem or this differential equation, this actually just looks like a harmonic oscillator, simple harmonic motion differential equation. So maybe we can demonstrate it during our live session if you want to review how to solve this differential equation. So you'll notice that they actually have the same form. In here you have positive k squared, in here you have negative k squared. So if you have a second order differential equation like this, and it's positive k squared here, then the solution of that could be a e to the kx, or b e to the negative kx, or hyperbolic cosine. Take note that these two are solutions. Any of the two are solutions to this equation. You can verify or check it for yourself. You substitute that. You substitute these two solutions in that equation, and you will notice that you will satisfy this equation. So if you have a positive k squared here, the solutions are hyperbolic cosine. Take note that hyperbolic cosine and sine functions can be written in terms of exponentials and vice versa. So basically these two are just the same solutions. Now if you have negative k squared, the solution of that is sinusoidal, or e to the I k y. So you can have these types of solutions or this type of solutions. Again, these two types of solutions are just the same, because you can write the e to the ikx or e to the iky in terms of sine and cosine, and you can conversely you can write cosine and sine in terms of e to the iky. So take note, if you will recall, Euler's formula, you can actually write e to the I theta as cosine theta plus I sine theta. So that's Euler's formula. And cosine theta can also be written in terms of exponential. It's e to the I theta plus e to the negative I theta over 2. So basically, these two solutions are just the same. It's just the exponential form, and this is the sinusoidal form. Similarly, for the x here, this is the exponential form, and this is the hyperbolic sinusoidal form. Okay. So you will notice for a two-dimensional Laplace equation problem, you can have 4 possible combinations. So you can combine this x and this y, or this x and this y, and similarly this x and this y, or this x and this y. So the question now is, for this specific problem, what x will we use? Is it the exponential form or the hyperbolic sinusoidal form? And what y will we use? Is it the exponential form or is it the sinusoidal form? Now, for every problem, you need to look at the boundary conditions first. So, for x, for instance, when x approaches infinity, the potential must be equal to 0. So, when the potential approaches 0, it could mean that x, the x function, approaches to 0. So, which of the two x's here can approach to 0 when x approaches infinity? So definitely you cannot use the hyperbolic cosine or hyperbolic sine function, because these are just repetitive. You don't know the value of this at infinity. But in the exponential form, when x approaches infinity here, for instance, for the second term here, when x approaches infinity, then e to the negative infinity, that's actually 0. It will approach to 0. So this means that for this problem, we need to use this x na solution, the exponential form. So how about for y? So if you will see, one of the boundary conditions states that at y is equal to 0, the potential is equal to 0. Now, if you use the exponential forms, so you have, when y is equal to 0, so you have e to the 0, which is 1, e to the 0, which is also 1. So it doesn't approach to 0. But here, if you use this, so y is equal to 0, that's 1. Y is equal to 0, sine 0 is 0. So it can be 0. So we need to use the sinusoidal form, because this is the only solution that can approach to 0. These two solutions doesn't approach to the exponential form cannot be equal to 0 at y is equal to 0. So for this specific problem, the combination of the solution is an exponential x and a sinusoidal y. So this will now be our starting general na solution. So our x is exponential, our y is sinusoidal. So again, take note, it depends on the problem. So you can have different combinations depending on the specific problem. So you need to look at the boundary conditions to know what type of x solution and y solutions will you use. Okay, so I will call this equation 1. So we'll now start utilizing our boundary conditions. So I will now apply boundary condition 1 to our equation 1. So as x approaches infinity, the potential must approach to 0. So that's the first boundary condition. So when x approaches infinity, this potential must approach to 0. So when x approaches to infinity, so this term here is e to the negative infinity, and that's essentially 0, because that's 1 over e to the infinity, or 1 over infinity, and 1 over infinity is essentially very small, or 0. So the second term will become 0 when x approaches infinity. How about the first term here sa x? So you will notice as x approaches infinity, kaning term na e to the x becomes e to the infinity. So this term actually, or the e to the e to the kx actually approaches infinity. So it will blow up actually at infinity. It will become very, very big. And we can, and how do we make this whole term here approach to 0? So we can actually easily do that if we set a equal to 0. This coefficient here, a, to be equal to 0. So that this whole term will become just 0. And the first boundary condition can be satisfied. So this is the answer to the first boundary condition. We must set a be equal to 0. And our general solution is now simplified to only, so wala namaning this term here is no longer needed. So you only have this term here, b e to the negative kx, and then the y solution. So the coefficient b, we take that into c. So b times d will also be f. So b times c, the coefficient is e, and b times d is now our f. So this is now our new simplified general solution. So take note, from the general solution, we apply the boundary conditions to start until we approach to the specific solution for this problem. So this is now a more simplified general solution. So it only has two terms now, and we only have how many unknowns? E is still an unknown, f is still an unknown, and the k here is still an unknown. So we have three unknowns, but don't worry, we still have three equations. We still have three unknowns, we still have three equations. This means that this is solvable. Okay, we now apply the second boundary condition to our simplified general solution, to equation 2. So at y is equal to 0. So at y is equal to 0, so when y is equal to 0, cosine of 0 is 1, so it's just e. And then y is equal to 0, sine of 0 is 0. Okay, and this potential must be equal to 0 because this is our boundary condition. The potential must be equal to 0 at y is equal to 0. So what does this mean? The term e to the negative kx cannot be equal to 0 because this is e to the negative kx. It can't be equal to 0. So therefore, e is the one equal to 0. So our general solution is now further simplified. So since e is equal to 0, so wala na siyang a term, and you'll just have this one, f e to the negative kx sine ky. So there are only now two unknowns left, the coefficient f and this constant k. So we now apply the third boundary condition to this equation here, which we call equation 3. At y is equal to a, the potential must also be equal to 0. So we are talking about the upper plate here. At y is equal to a. So at y is equal to a, so alis na natin ang y with a. So at y is equal to a, the potential must be equal to 0. So of course f cannot be equal to 0 because f, if your f is equal to 0, then your potential is 0. 0. And then e to the negative kx can also not be equal to 0. So this means that the only thing that will be equal to 0 is sine ka. So if the sine of something, of an angle, is equal to 0, what can you say about the angle? So in this case, ka. So if sine ka is equal to 0, then what can you say about ka? So ka must be a multiple of pi, because sine of pi, sine of 2 pi, sine of 3 pi, sine of 4 pi, those are 0. So we can see here that k is, from this equation, we can now solve for the value of k. It's now n pi over a, where n is 1, 2, 3 are integer values. By the way, we will not include n is equal to 0 here, because if you include n is equal to 0, that would mean your k is equal to 0. And if your k is equal to 0, sine sa 0 is 0. So your potential is 0. So actually, the V is equal to 0 and a solution is most of the time always a solution, because 0 is most of the time a solution to every equation. It's what we call the trivial solution or the obvious na solution. So we will not include the trivial or the obvious solution. So we'll just have n from 1, 2, 3, and so on. So we'll not include the V is equal to 0 solution. So we will use this value of k here and substitute that to our equation here. So our equation will now become like this. So we substitute k as n pi over a. K is n pi over a. But take note, since k has different values, this means that we also have different values, different solutions, or more than one solution for the potential. Hence the summation term here. So we have more than one value of k, which means we have more than one value of v, because n here can have a value of 1, 2, 3, 4, 5. So there are many solutions to this problem. And since these are all solutions, then any linear combination of this solution is also a solution. So our most general solution now is the summation of all of those solutions. So we now have a summation here, the summation of all solutions, to take into account that we have different solutions, n. So n can be equal to 1, 2, 3, 4, 5, and so on. So this is now our most general solution, the linear combination of all the possible solutions. So we sum it all. So the f here, instead of one value, we now have to solve for the many values of f, f1, f2, f3, f4. So these are now what we call the linear combination coefficients. So how do we now solve for the different values of f sub n? So of course we still have one last remaining boundary condition. So we apply that boundary condition to our general solution here. So at x is equal to 0. So at x is equal to 0, e to the 0 is 1. So we have this equation. So at x is equal to 0, it's equal to VO at a function of y. So how can you solve f of n here? So you will notice this is actually just a Fourier sine series. Fourier sine series. So meaning we can actually use the Fourier series, take advantage of that. So Griffiths will call this next solution as Fourier's trick. So in the Fourier's trick, you will actually, so we will now focus on just this equation. And in the Fourier's trick na solution, we multiply both sides by this term, sine n pi y over a, and then integrate over dy. So that's what we did. We just multiply both sides of the equation here by sine n prime pi y over a, and integrate over dy, where y is from 0 to a, our boundary for y. So you do that and you will achieve this equation. So this integral here is now familiar. You have sine n prime pi y over a, sine n pi y over a. This is just the orthogonality condition for the sine, and this is just equal to a over 2 Kronecker delta n prime. So this whole integral here is just a over 2 delta n prime. So what does this mean? Since this is a summation, we are summing all of the possible values of n, but there is a Kronecker delta here that limits this summation. Now this will mean that only one term in the summation will survive. N is equal to n prime because the value of this canonical delta is 0 if n is not equal to n prime. So thank goodness, thank God for this canonical delta here. We can get rid of the summation now. So since only one term in the equation will survive, then our equation will just become fn or fn prime. Anyway, n must be equal to n prime, and then you have a over 2, and it's equal to that integral of VO sine. So we'll now, instead of n prime, we'll just use n because n prime is equal to n. So n pi y over y, over a dy from 0 to a. So to solve for fn, we just cross multiply the a over 2, so 2 over a. So again, that's the Fourier's trick. The Fourier's trick is to multiply a certain value so that you can achieve the orthogonality condition. It's not always that you multiply sine n pi y over a, okay? It depends on the ano, so that you can, if it's cosine, then you multiply it by cosine, so you can achieve the orthogonality condition for cosine or any orthogonal functions for that matter. So okay, so you will get this this value for fn. So we cannot solve for fn unless we can solve this integral here. And we cannot solve this integral here unless this function v naught as a function of y is specified. So for instance, suppose voy is just a constant v naught. So if it's just a constant v naught, then we can take it out of the integral because it's no longer a function of y, and we have this integral. So this integral here is just a very simple integral of sine theta. So you just change variables. So you let u is equal to n pi y over a. So you will have a factor of a over n pi du. So you have a factor of a over n pi, integral of sine theta or sine u du. And evaluating that will give you 1 minus cosine n pi. Now, this value, this cosine n pi, cosine of n pi can have a value of 1 or negative 1. So when n is odd, for instance 1, 3, 5, 7, the value of cosine n pi when n is odd is negative 1. When n is odd, so 1, 3, 5, 7. So cosine sa pi 180 degrees, negative 1. Cosine sa 3 pi, also negative 1. Cosine sa 5 pi, also negative 1. When n is equal to even, so 2, 4, 6, 8. So cosine sa 2 pi is positive 1. Cosine sa 4 pi is positive 1. So the value of this term here could be positive 1 or negative 1 depending on n is even or n is odd. So when n is even, so cosine sa n pi is positive 1, and then you will have 1 minus 1 is 0. So your f of n is 0 or n is equal to even. And when n is equal to odd, so cosine of n pi is negative 1, so 1 minus negative 1 is positive 2. Then we can now generalize the values for fn here. So it's actually 4v naught over n pi if n is odd, and if n is even, 0. So meaning, what does this mean? Walay even fn na coefficient. So there's no f2, f4, f6, f8. They are all 0. But na ay f1. For example, f1 is what? F1, based on this formula, F1 is 4 V naught over pi. And then, of course, F2 is equal to 0 because even. And then F3 is So you have n is equal to 3, so 4 v naught over 3 pi, and then f4 again is 0 because it's even. So when I pasabot ani nga, this is what these results imply. There are no even fn's, only odd fn. So f1 is 4 v naught over pi, f3 is 4 v naught over 3 pi. Okay. So going back to our general potential, so we just substitute this value of fn here in this general summation, and this is now our potential. So 4v naught over n pi, but since we are summing over n here, so the 1 over n factor here is inside the summation. All of the terms containing n are inside this summation. So n starts from 1 and n must be odd. So this means that only odd terms are in this summation. So 1, 3, 5, 7. So 2, 4, 6, 8 are not included because their fn's are 0. So this is now the specific potential for this problem. So basically that is separation variables in Cartesian coordinates. Okay, I will just go through with this problem very quickly, since we all now have experience how to solve the potential using separation of variables, but that is actually just in two dimensions. So this is an example of two infinite grounded metal plates and two metal plates forming a box. So we have the upper and the lower plate here. These are our grounded metal plates and they extend to infinity. And we have two metal plates at the sides, but they are not grounded. They actually have a potential V naught. So V naught is a constant potential. So two sides are maintained at a potential V naught. Two sides are grounded. They have 0 potential. Of course, there are insulation layers in between the plates to prevent them from shorting out, or to prevent the charges from flowing from one plate to another. So we are now asked to find the potential inside the box. Okay, boundary conditions. So this is a box. A box has 6 boundaries. So first boundary condition, at y is equal to 0. So we are talking about the lower grounded plate here. So the potential must be equal to 0. At y is equal to a, we are talking about the upper plate here. So that's at y is equal to a. So that's also grounded, so that's b is equal to 0. And then at x is equal to b, the potential is v naught. So this side here, x is equal to b. And at x is equal to negative b, the potential is also v naught, and this side here. So this is still a two-dimensional problem, so I will just go through with this very quickly. So you have the same solution, separable solution. The potential is only a function of x and y, so meaning it's a multiplication of two functions x and y. Okay, we choose the hyperbolic cosine for x because we have there's no 0. There's no 0 for x. So when x is equal to b or where x is equal to negative b, the potential doesn't go to 0. So we will now prefer to use the hyperbolic sign for x na solution. We will not use the exponential solution. And for the y solution, since there's a y is equal to 0 here, where the potential must be 0, we'll still use the sinusoidal na solution. So this is just one of the 4 combinations for the two-dimensional Laplace nga solutions. Now, if you'll notice here, there is a symmetry along the x-axis from negative b to positive b. This means that the potential along the x-axis, which is described by this function x, this function x must be symmetric. Again, when you say symmetric, you mean that it's an even function. So what does an even function look like? So like a parabola, for instance. So if you have a parabola, so something like that. Sorry for my drawing. If this is negative b, this is positive b, the value at x is equal to negative b, the value of y, for instance, at y is equal to negative b and y is equal to positive b, the value in the y-axis is the same. That's what we mean by a symmetric or even function. So they are symmetric in both sides of the interval, or both sides of yes, the boundary. So a cosine, for instance, a cosine function is an even function. So cosine starts from 1, so that one, that's an even function. That's a cosine, that's the graph of a cosine. But the sine is not, is an antisymmetric function, it's not an even function. So the graph for sine is actually like this: 0 at x is equal to ano, so it's antisymmetric. This is the graph for sine. So the same is also true for hyperbolic sine and hyperbolic cosine. So the sine is not an, this is not an even function, and we require x to be symmetric or even. So only cosine should be the solution, and in order to do that, we must set b is equal to 0, because we only need even or symmetric solutions. So our solution is now reduced to this one. So we need we only have 3 unknowns: k, e, and f, and we have actually 4 solutions. So that's the thing also about even functions. You only need to use one side of the function, because the other side is just symmetric. So we only need to use actually up to 3 boundary conditions. So the x is equal to negative b, is this boundary condition is actually unnecessary because of the even symmetry, or because of the symmetry. So we only have 3 unknowns: k, e, and f. So we only need these 3 boundary conditions. So you will do that by yourself. You do that by yourself, and you will get this specific potential for this specific problem. Okay, so let's now have a 3-dimensional example. So this is an infinitely long rectangular metal pipe with grounded sides. So it's still a box, a very long box, where 4 of its sides are grounded, but one side is not grounded, and one side is at infinity. So we will assume that the potential on that side is 0. So we are asked to find the potential inside the pipe. So take note, all of the sides of the pipe is 0, including the one with infinity, even though it's not grounded, but it's at infinity. So the potential on the 6th side is 0, and the potential on this side is still unspecified. It's b naught as a function of y and z. So this is a 3-dimensional problem. So you will actually have 6 boundary conditions for this problem. So these are the boundary conditions. So at x approaches infinity, b must approach 0. So we are referring now to the 6th, or the last side of the box, the side at infinity. And y is equal to 0, y is equal to a, z is equal to 0, z is equal to b. So we are pertaining to the 4 sides here. The one in the upper side, lower side, the front, and the back. They're all grounded, so their potentials are all 0. And at x is equal to 0, we are pertaining to this side here. So this is the x-axis, this is the x is equal to 0 na plane, the yz plane. It's actually v naught, which is a function of y and z. So this is now a 3-dimensional problem. So we need to have the 3-dimensional Laplace equation. So our potential will be a function of x, which is a function of x, y, and then z. So this is our separable solution. So you do the same, you substitute this in this equation, you divide by x, y, z, and you will have an equation like this. So actually in the previous 2-dimensional problem, we only have like this. And then we let that be equal to k squared. So that's what we did in the previous 2-dimensional problem. But since this is now 3-dimensional, we now have an extra term here, and we will let that extra term be a constant L squared. Take note, this is a function of x. It's equal to a function of y plus some function of z. And that could only mean that it must all be equal to a constant. So the constant here is k squared plus L squared. So therefore, x will be equal to k squared plus the function of x will be equal to k squared plus L squared, where k and L are constants to be determined later. So from this partial differential equation, we now have we can now have three differential ordinary. From partial, it becomes now a total or ordinary differential equation. So this is the differential equation in x, in y, and in z. So again, these types of second order differential equation is just similar to a harmonic oscillator equation. So if positive ang imong constant here, then the solutions of this are hyperbolic functions, hyperbolic sinusoidal functions. And if negative ang imohang, if you have negative constants here, then the solutions to this are sinusoidal functions. So for the x solutions, we can have two options. We can use the exponential form, or we can use the hyperbolic cosine form. For the y na solution, we can also have the option of using the exponential form, or we can use the the sinusoidal forms. Similarly with z, we can use the exponential form or the sinusoidal form. Okay, so you will notice that there are a lot of possible combinations of x, y, z here. Actually, to be precise, there are 8 possible combinations. So in the 2-dimension, you only have 4 possible combinations, but in 3-dimension, you now have 8 possible choices of solutions. So in the same manner with the 2-dimensional problem, we need to consult the boundary conditions as to what type of solution will we use. So for example, for x approaches infinity, the potential must approach to 0. So obviously, we need to use the exponential form. For y approach when y is equal to 0, v is equal to 0. So we need to use the sinusoidal form. So sine of y is equal to 0, sine of 0 is 0. And similarly for z, we also need to use the sinusoidal form. Okay, so our potential will now be a combination of these three. So I will no longer write this because this is very long. You can also do the same, provided that you specified what is your x na solution, y na solution, and z na solution. Okay, so let's apply the first boundary condition. As x approaches infinity, the potential must approach to 0. So instead of writing the whole potential, when the potential approaches to 0, and when the potential is equal to x, y, and z, and since we are only talking about the x na boundary condition, so when v approaches to 0, it's just equivalent to saying as the function x as a function of the variable x must approach to 0. So that one. So v approaches to 0 for the x boundary condition, it just means the function x approach to 0. The same for y and z. So this means that the function x must also approach to 0 in order for the potential to be approaching to 0. So again, this term here will be 0, e to the negative infinity. When x approaches infinity, that's 0. Again, this term here will be e to the infinity. It will actually become infinite. It will blow up. So in order to satisfy the first boundary condition, we need to set a to be equal to 0. Because unless a is not equal to 0, this term will become infinity. This will blow up when x approaches infinity. So therefore, our x will just be simplified into a single term here. So our x na solution will just be this term here. A is now equal to 0. So we'll call that as our equation 1. Then we apply the second boundary condition. At y is equal to 0, the potential is 0. So it's c cosine ky plus d sine ky. So when at y is equal to 0, the sine term will become 0, the cosine term will be equal to 1. So this means that c plus 0, or c is equal to 0. So c is equal to 0, meaning your solution will just be purely d sine ky, walay cosine na solution. So this is our equation 2. So we apply boundary condition 3 to solve for the value of k. So at y is equal to a, this is the boundary condition 3, the potential must be equal to 0. Again, d must not be equal to 0. And so this means that sine ka must be equal to 0. And similar with what we did in the previous example, ka must be equal to a multiple of pi, and k must be n pi over a, where n starts from 1. So again, we don't include the obvious or the trivial solution that will make our potential v equal to 0. So v is equal to 0 is always a solution to everything. So this means that our y na potential will just be d sine, we now have our value for k, n pi over a y. So you do the same for z and b. You apply boundary condition 4, and you will see that only the sine component will survive, and you apply boundary condition 5 to solve for L. So you do that for z, so you will notice that only the sine component will survive, and you apply boundary condition 5 to find the value of L. So L is actually in this case m pi over b. Again, we don't include L is equal to 0 na solutions, the trivial or the obvious solution. So this is now our z na solution. So we combine all of the solutions x, y, and z, and we now have this general potential function. So our x is exponential, e to negative x. Our y is sinusoidal, our z is also sinusoidal, and we combine all of the constants to g. Now, since n and m have more than one values, this means that we now have more than one solution. And in order to take into account that the many solutions of our v, we need to sum all of the possible solutions. So we combine, or we linearly combine all of the solutions for v. So we sum over n and we sum over m. So this is now our most general solution. So you apply the last boundary condition to that to solve for g in the same manner with the two-dimensional case that we have discussed. So again, you use so this is at x is equal to 0, the potential is v now. So at x is equal to 0, so you have e to the 0, that's just 1, so mawala na siya nga term, and you are left with this. So again, you use Fouriers trick, and then multiply both sides by sine n prime pi y over a and integrate over dy, and multiply both sides by sine m prime pi z over b and integrate over dz. So you will have two integrals here. So you will have an orthogonality condition over dy and over dz. So you just repeat the process in the previous problem. Okay, so doing that, in doing that, you will, when you use the orthogonality condition, you will encounter a Kronecker delta function again, and in these two summations here, only one term in the m summation will survive. M is equal to m prime. Similarly, in the summation for n, only one term again will survive. N is equal to n prime. So actually, in this side here, you will have g and m, and you will have a over 2 for the first integral and a over 2 for the second integral. So you will have a squared over a over 2, and the second integral is actually, since this is b, z is evaluated from 0 to b and y is evaluated from 0 to a. So you have a over 2 and then b over 2, so you have ab over 4 na constant, and you cross multiply that, so you have 4 over ab. So this will be your integral on the right side of the equation. So you multiply both sides by sine m pi z and n pi y, and integrate over y and z. So you cannot solve this integral unless this potential function v naught as a function of y and z is specified in the same manner with our previous problem. So suppose that potential is given and say it's a constant, so meaning you can take it out of the integrals. So you are left with these two simple integrals. So you have sine u du here, sine u du here. So this is actually just similar to the previous problem. You will have the answer for this will be b over m pi, then 1 minus cosine m pi, and this one is a over n pi, 1 minus cosine n pi. And these two integrals will be 0 unless n and m are both odd. Because if any of these two are even, if n is even, then this is 0 and the whole integral becomes 0. So the answer for this will be this one. If both of them must, the condition is that both n and m must be odd. Because if any of them is even, then the answer is 0. So this will now be the general solution for this problem. So n here and m here are both odd functions. So this is a double summation. So this is actually a very long summation if you try to expand this summation. But anyway, this is our final answer. No need to expand this summation. Don't ever expand a double summation. You're just trying to hurt your brains. So that's it for the separation of variables. It's actually a very long topic. We are now 1 hour into this lesson, but essentially it's a long process. Sometimes it's a long process, but the process is just the same. So you assume separable solutions, you substitute the separable solutions to the Laplace equation, and then you separate the partial differential equations into ordinary differential equations, and you solve the solutions for each of the coordinates. So again, consult the boundary conditions to know which solution, whether it's the exponential or the sinusoidal forms, must be used. So that depends on the boundary conditions. So that's it for the separation of variables in Cartesian coordinates. It's a very long process. So I will see you again for the next part of this technique, which is separation of variables in spherical and cylindrical coordinates, which I think will be much easier. Actually, the spherical coordinates is much easier to handle with, but the cylindrical is not so easy to handle with. Okay, so that's it for this lesson, and I will see you again next session.